Before any tower rose above the water, the Akashi Strait was already a problem. Strong tidal currents, deep water, and one of Japan's busiest shipping channels stood between the two shores. To cross it, engineers could not simply build a normal bridge. They had to ask one question: how was it built step by step? The first step was not construction, it was investigation. Survey vessels mapped the seabed, sonar traced the underwater terrain, and geotechnical crews studied the ground where the foundations would have to sit. Every current, depth change, and navigation route had to be understood before the bridge line could be fixed. A bridge with many piers would have blocked the shipping channel and exposed too many foundations to fast water. So the design moved toward a long-span suspension bridge, two main towers, massive anchorages on land, and one open central span over the strait. Once the plan was locked, the construction site moved offshore. Tugboats, barges, floating cranes, and positioning vessels entered the strait. But even staging the work zone was difficult. The current pushed barges offline, and every vessel had to be held in position before foundation work could begin. The foundation phase began below the surface. Crews prepared the seabed, removed unstable material, and checked the final level where the caisson would land. This was the hidden part of the bridge, but it would carry everything above it. Then, the giant steel caisson was towed into position. Floating cranes began lowering it through the moving water, while tugboats and survey teams controlled its alignment. A small error at this stage could shift the entire tower position above. The current did not stop for the engineers. As the caisson settled, tidal force pushed it slightly offline. Tugboats corrected the movement inch by inch, turning a dangerous drift into a controlled positioning operation. After repeated checks, the caisson finally seated onto the prepared seabed. The foundation base was now in place, but it was not yet protected. Around it, the same current that made placement difficult could still scour the seabed away. To protect the foundation, crews built a rock armor layer around the caisson. Barges released heavy stones into the water, forming a protective ring against scour. Under the surface, the rock layer spread across the seabed, reducing the force of the current around the base. With the foundation secured, the bridge finally began to rise above the sea. Steel tower segments arrived by barge, were lifted by floating cranes, aligned over the foundation, and fixed into place with heavy bolted joints. This was the first visible sign of the structure. Segment by segment, the first tower climbed higher. At the same time, work began at the second tower site. The bridge needed both towers to grow in balance before the cable system could begin. At this height, wind became a construction risk. A suspended tower segment could not be forced into place during unstable conditions. Engineers paused lifts, checked vertical alignment, and waited for safe limits before continuing. The towers continued upward until both main towers reached their completed construction height. No deck existed yet, and no main cables had been spun. But the two steel towers were now ready for the next critical step, crossing the empty span with the first rope. Before that rope could be pulled across, the towers had to be checked again. Wind speed, vibration, and structural movement were measured at height. Only after the towers passed these checks could the cable installation phase begin. The first connection across the span was not a main cable. It was a thin pilot rope. A helicopter carried it from one tower toward the other, creating the first physical link across the open air above the strait. That pilot rope allowed crews to pull more temporary lines across the span. From those lines, they built a narrow catwalk, not a roadway, but a temporary work path suspended high above the water. It gave workers access to the route where the main cables would be formed.
Safety harness check complete. All clear on this section. Copy that. Wind level steady for now.
With the catwalk ready, cable spinning began. Thin steel strands were pulled across the span and guided over the saddle at the top of each tower. Each strand followed the curve that would eventually become the bridge's main cable. One strand was not enough. Thousands of individual wires had to be pulled, tensioned, and grouped together. As the process repeated, the loose strand bundle grew into the shape of a main suspension cable. After the strands accumulated, machines compacted them into a dense circular cable. Engineers inspected the cable at the tower saddle, then applied protective wrapping against corrosion. Only after this could the bridge move toward hangars and deck construction. Then construction had to pause for another reason: post-earthquake checks. Engineers inspected the towers, foundations, main cables, and geometry of the span. This was not a collapse scene. It was a precision recheck, making sure the next lifting operations matched the adjusted structure. Once the cable system was cleared, vertical hanger cables could be installed. These hangers dropped from the main cable toward the future deck line, forming the suspended curtain that would eventually carry the steel girder blocks. The first steel girder block arrived by barge beneath the span. Floating cranes lifted it into position, workers controlled it with tag lines, and engineers aligned it beneath the hangars. Once connected, the first block was secure, but large gaps still remained on both sides.
Tension the south tag line.
Roger, tensioning now.
Alignment confirmed. Secure the connection points. Tension coming up on the main hangars. Hold steady. Roger that. Crane, ease the tension slowly.
Even during deck lifting, the strait kept interfering. Tidal current pushed the barge below the span, forcing tugboats to hold it in position before another girder block could be lifted safely. More girder blocks were lifted and connected, extending the suspended deck outward. At mid-span, one of the most delicate lifts brought the structure closer to closure. By the end of this stage, only the final gap remained. The final steel block was brought in below the open gap. Cranes lifted it slowly, while survey teams checked alignment from both sides. Workers bolted the last connection, and the raw steel deck became structurally continuous for the first time. But a closed steel structure was still not an operating bridge. The road systems, barriers, joints, drainage, and surface layers still had to be built. Crews began turning the raw steel deck into a roadway. Expansion joints were aligned, drainage systems were installed, and barriers were secured along the edges. These details would control movement, water, and safety once the bridge entered service. Then came the road surface. Paving machines placed asphalt across the prepared deck, and rollers compacted it into a smooth layer. In time-lapse, the exposed steel structure changed into a finished roadway, but it was still closed for testing. With the road systems in place, the bridge was ready for its final engineering tests, not yet for public traffic. Engineers set up sensors and survey instruments across the deck. Official test vehicles moved slowly into measured positions, applying controlled loads while crews recorded how the structure responded under weight. The inspection continued through the bridge's operating systems. Expansion joints were tested, water was run through the drainage paths, hanger connections were checked, and the protected main cable system was inspected one last time. After the final measurements were confirmed, engineers closed their inspection cases. The bridge had passed from construction site to completed structure. Only now does the full bridge appear. Across the Akashi Strait, the completed suspension bridge stands on two main towers, with sweeping main cables, vertical hangers, and a roadway stretching from shore to shore. Traffic moves across the deck, while ships pass beneath the long central span. The same open channel that made construction so difficult is exactly why the bridge had to be built this way. From seabed foundations to towers, cables, deck, and testing, the natural barrier was crossed one engineering step at a time.